Okay, I'm going to talk about the compacticity, and here is the outline of that talk. I will mention basics of transient current technique. So for those who may not be so familiar with the concept, then I will list examples of analysis of measured currents, and we will concentrate mostly on silicon. So we'll have a look at how you see the space charge, how you can determine the full depletion voltage, charge collection efficiency, effective trapping times, let's say mobility, and you can see the effect of changing resistivity. So these are all, I would say, educational examples, but don't be, let's say, led into the conclusion that this is only for educational purposes. This, if you are doing a material study, these are really very meaningful measurements. The third part of the talk will be about the setup and its operation. It will consist of some videos, so we will have a look how this is operated, and then we'll have another part of the talk which will be on examples of data taking. So again, you'll see how the curves look like when they're taken, and there will be a slide on analysis tools at the end, really a single slide, and then the conclusions is actually invitation for your questions. So let's go to the basics of transient current technique. It was actually introduced or dates back in the 60s, and the technique itself is basically observing effects of non-equilibrium carriages in different devices. So if you look at it, this is what we usually consider a simplified view of a detector. So you have two plates, cathode and anode. You have a medium in between which gets ionized. In this case, this is semiconductor. And then you have the electrons going one, the holes going into another direction. And what you actually look in transient current technique is the current induced. Most of the applications in high energy physics uses the charge, so how much charge you collect. And the advantage of looking at the current is, of course, that you get much more information about your sensor. So from 90s on, the technique was widely used in studies of semiconductor detector materials, mostly PET detectors at the beginning. So the affects the changes of the space charge after irradiation of devices, for example, trapping times, charge collection. There are many studies that were that exploited the benefits of the TCT. Then in the recent decade, the use of scanning TCT, so the ones that I introduced in the first talk, where the focused laser beams are used, are getting way more popular for obvious reasons, because you can actually study strip, pixel, 3D sensors, whatever device you have in mind, and you can access it with laser. You can, of course, look into it. Let me just tell you what we are going to look now. We are going to explain some basics, so how what the current in TCT means, give some practical advices using or customizing a TCT system, then some examples of what can be done with TCT, and then really the core is the introduction to this compact TCT. So if you want, in short, this is the TCT. So you have a sample, you have a laser plus optical system which shines on the surface of the sample. It basically, what you want is to mimic, here in the bottom you can have a look how the particle ionizes the sensor. You want to do the same or similar thing with the laser. The next thing is the how you connect your electrodes to the electronics. remember, we want to look at the currents, and the currents are of nanosecond order. So you really need to have high bandwidth components, and it's not as simple as it looks like a resistor and a capacitor, as you can imagine. But this is basically what it is. And then you have a fast transient current amplifier. And the third part is a digital oscilloscope or a digitizer. And that is basically it. So it has 3 components. And you can study a lot of things with it. But this system can also be used with, instead of the laser, you can use the alpha particles. I will show you one example of that. Or you can use the microbeam. And there are plenty of examples, but I will not show them today. So, and then you get basically the same thing. So, like I said, the normal or the TCT that we are looking today uses laser. And as you can imagine, laser has many advantages over the particles. I listed 5 of them, the most obvious ones. So if you have a laser, there is no problem with noise, right? Because you can average and you can repeat you can shoot as many pulses as you like, and to get the shape of the signal in your sensor. So this is a good thing. The other thing is you can trigger it, so you know exactly when the laser pulse comes, so you know exactly when to look at your signal. You can use different wavelengths of laser, and that means different penetration depth in your device, in this case silicon. You can tune the intensity basically from few photons to huge amount of let's say electron hole pairs, so large deposited energy. And you can, to some extent, even in the compact TCT, control the beam position. So what does that mean? How fast should the pulses be? They should be of order of 100 picoseconds. So if you connect any reasonable electronics to it, you will introduce the RC, which is likely of order of few hundred picoseconds. So going to femto for the signal formation alone, there are other effects which maybe femto lasers are much better, but for going to femto just to have a faster pulse with the normal devices, it does not present a high or very significant advantage. What you have to pay attention with the laser, and this is usually the case, is that you don't have any bleeding. So the pulse laser should really have no photons outside the pulse itself. So it cannot be that you just modulate it or something. It really needs to be without any photons outside of the pulse. That is particularly true if you're looking at some very cold operation. So the lasers look very promising and advantages, have a lot of advantages of the particles, but you should not forget that if you use wide bandgap semiconductors, so if you use, for example, diamond, it's very difficult to get the laser that has enough photon energy. Then you have different effects due to the laser pulses. If they're focused, you can create a lot of charge, and you can have screening effects, or plasma effect is called. And of course, the most important one is that if you want to study the structure that is underneath the metal, you cannot access this with laser. So it's much less, you need to design your devices with this in mind. Let's just have a look at the laser flavors for silicon, for example. So if you go to 160 nanometer, your laser goes 1 millimeter into the device. So this is indicated here. And this basically mimics the minimum ionizing particle. So it deposits the roughly homogeneous amount of electron hole carriers, electron hole pairs along the track. If you go lower, with if you reduce the wavelength, it penetrates less and less and less, and at 405 nanometers, which is currently the smallest wavelength that we have with our lasers, you are at around 100 nanometers. Now, in recent, let's say, years, other materials are getting popular or even very popular, like silicon carbide, gallium nitride, and to some extent, okay, diamond. And at least for these two, we are now getting into, so this is the band gaps. So we are getting close to the wave, the laser diodes that we are using are getting close to the required wavelengths to actually use also TCT with these devices. So it looks very promising also for other semiconductor materials. So how do we connect this electrically? There are two configurations which both can be used in the compact TCT. The default one is with bias T, which means that you actually have everything at ground and you bias your sensor and read it out from the top. This has a lot of practical advantages. It's much easier to ground, shield, cool, but it's not so appropriate if you, for example, would have, let's say, two electrodes. So for multi-channel operation, there you would need to put high voltage at the backside, and then you can use it without the bias T, but it's much more difficult to realize the connections. So if you look at what the electronics components need to fulfill, you need to have first, like I said, they have to be, the bandwidth should be very large on both sides, on the low and on the high, so that you can reproduce your currents as much as possible. So the true induced current is then what you measure is actually corresponds to that. It has to stand the bias T if you're using it, really high voltages, 1000 volts or so. The amplifiers can be of different amplification, depends what you want to do and how your digitizer or digital oscilloscope looks like. So can go from 20 decibel to 53 decibel. And what you should pay attention in connecting all these things is that everything is shielded with as few patch connections as possible, that you have a very good impedance matching so that you don't get the reflections distorting your signals. Now this is the part on the introduction of the TCT. Now we move to examples of measured currents. So most of the samples that we use look similar to that. So this is a silicon diode, quite an old one, but you can have all sorts of devices. What is important is to have this opening in the metallization where the light can enter. And if you look at how the detector is now sketched, so you introduce, if you use the red light, you create electron hole pairs at the top, so here. And then the electric field pulls the electrons back. This is the N-type P on N diode, let's say of 300 micrometers for this study. And you can observe the currents. So the current that you observe is actually given here. You can see many terms. One is the number of electron hole pairs that you create. This term actually comes into the game only when you have damaged sensors. We'll come to that later. The most important is that what you measure is actually the velocity of moving electrons. And from that, you can then conclude on the electric field and on the full depletion voltage, on many things. So let me show you. So there are some illustrations of how this looks like. So you create and you can see how the holes in this case, if you inject the light from the back, drift. You see, basically if you use the short wavelength, you look only the movement of holes. If you use it from the top, you can only look the movement of electrons, and you can nicely see how these currents look like. Yeah, so you see this is a high resistive PN diode, so the space charge is very low, and you get very nice examples of long signals over 100 nanoseconds, and you can see that, for example, in this case, the current rises because the electric field rises. The junction is here, so it moves from low field to high field. If you inject from the top, you actually move from the high field to the low field. So this is better shown here. So if you inject hole here, so you create these electron hole pairs here, electrical field pulls holes to the other side, and as they move into ever higher electric field, remember the electric field in reversely biased silicon diode is, let's say, linear, and you can nicely see this linear behavior also in your signals. So you can see also the diffusion, so the longer the drift lasts, the more the carriers diffuse apart and the longer the tail. And if you look at for the front injection, so you see the opposite picture. So now you inject in the high field, and as they move to the other side, they see less and less electric field, and then they finish their drift. So basically, this is the whole thing. What we learned now is we already know how to determine the sign and, to some extent, the shape of the field, because the field has the same shape as the current, right? So this is a very important study. So it tells you that whatever you find in the silicon textbooks about the field in the diode is actually true, and you can easily check it in a most, let's say, simple way. Now, this is a bit off, maybe not so educational, but what we studied in the past is radiation damage of this. So once they are operated in different environments, they change their properties. And this is example of the same diode as you've seen before. Remember, before the current for the whole injection was low, and then it increased. As you can see that after some damage, the same current has a different shape. And this was, let's say, some 30 years ago when it was first discovered. It was called the space charge sign inversion in damaged silicon. And you can clearly see how, nicely see how this can be measured and observed. And then if you look from the front injection, you see exactly the mirror image. So again, now we introduce the electrons in low field and they go to high field. And what was very, let's say, heavily studied some 20 years ago was this so-called double junction, where you see slightly higher field here, and then you have a minimum in the field, and then you have again the rise in the field. So all this can be relatively easily seen in such a system. Of course, now if you want to, like I said, if you want to simulate your minimum ionizing particle, so this is what you measure, and this is you have to use the infrared, so 1060 nanometer wavelength, and you basically, what you see here is this triangular shape. So this is coming from electrons, this is coming from holes, and this is then the sum of both is the red, and this is triangular shape you see. Later in the fifth part of the talk, you will see the measurement of this. You will see exactly how it's actually measured on the screen. What people mostly use the particle detectors is to integrate the charge. Of course, now if you have the current, there's no big deal. It's not the big secret that you get the charge that is collected by such a device by integrating the current. And the nice thing is that you can actually, if you do the analysis offline, you can change this integration time window, and you can explore things like ballistic deficits. So if you say your electronics in real life maybe will integrate only 20 nanoseconds your signal, then you can see how much charge you can lose if your signals are longer. So all these things are, of course, immediately obtained from the shape of the current. So in this case, for example, this is the red laser. You can also see that the charge is actually even below the full depletion. It's almost 100%. I don't want to go too much into that, but this is something that was that is well explained by the semiconductor device physics. And then maybe more interesting is if you look at the whole injection, so you inject from the back and you can clearly see you get no charge, and as long as the device is not depleted, so when the electric field touches your back, then you get the full charge. So this is a very nice way of knowing when exactly your device is fully depleted. Another thing was, for example, if you want to study the effects of the undepleted bulk, so that's some more elaborate physics, you can actually use the infrared light, and you can see clearly that if you want to have for non-irradiated device or for non-damaged silicon, the full depletion can be nicely determined by having charge versus square root of bias voltage, and if it's irradiated, it has to be the bias voltage. Like I said, this shows that how the undepleted bulk resistivity changes with radiation, and it's also something that you can nicely see in the TCT from these shapes. Yeah. So one of the studies that is usually done at the ICFA school, these setups, the compact TCT is also used at ICFA, this is instrumentation school for particle physics, is the mobility measurement. So if you have a high resistivity silicon diode, you can actually, so it looks like that. So this is the electric field profiles, different bias voltages. So this is under depleted, this is just depleted. And then as you increase the bias, the electric field shape looks like that. And if you are high enough with the bias, you can say, okay, I have a small difference between the maximum and the minimum field. I can approximate with the average field. And if you do it, then you can say the drift velocity is just the thickness of your device divided by the drift time. So drift time is usually defined as a full width at half maximum of your pulse. All the examples that I'm showing are on the same sample. So all the measured plots are on the same sample, so you can directly compare them. And then if you say that your velocity is mobility times the electric field, then you say, okay, I have an average electric field bias voltage divided by thickness, then you can actually measure the mobility by simply measuring, by knowing the voltage, thickness, and measuring the drift time. And this is something that students do, and they actually measure the mobility and also the saturation velocity, and then you can heat or cool your sample, and you can measure also the effect of the temperature on mobility. So a lot of semiconductor physics in a very simple with a very simple measurement. So what I wanted to show you, since I mentioned that we can also use the alpha particles instead of the laser, if you have, for example, if your lab or your practicum exercise at the university has a americium source. So this is, for example, the single crystalline diamond using this method. You see that there is basically no space charge. So this is really a linear field in the diamond, and you can see how the pulses come together. And if you use this method, this is the mobility parameterization in diamond. So you can see, unlike in silicon, the holes are more mobile than the electrons. So a very simple measurement, but it has a lot of physics inside. One of the things that TCT became very well known for is the trapping. So if you have silicon with defects, this is something that you can well study with it. This is just an example of determining the trapping of the drifting charge. So As you've seen in the previous slides, as soon as the diode is fully depleted, you get a constant charge. Of course, you collect all the charge you generate in your sensor, but in damaged silicon, this is not the case. So this is where the default depletion is. And then if you apply higher bias, the charge still rises. The explanation is very simple, and it's illustrated here. So you generate electron hole carrier, free carriers, and as the electrons move, so here are generated, they start to move, and if you have a damaged silicon, some of them get trapped, and as they get trapped, they don't induce current anymore, and you get less charge collected at the end. And this is described by this, the probability of this trapping is 1 over the trapping time. So the less time the carrier spends in your sensor, the less likely it is going to get trapped. And this is this exponential term. And what you can do, you can exploit this rise here to determine the trapping time by simply what you measure, you correct for the exponential with this time constant. And if you did it right, then you restore in this corrected waveform, you restore this the fact that above the full depletion voltage, your charge should not change because you collect all the charge. And if you don't do it right, you get either more charge at lower voltages or more charge at higher voltages. When you do it right, it's flat, and this is the measurement of the effective trapping time. So there were a lot of studies done. I have a list of the publications that use that. So this is the list. So there are just few examples. There is a very long list with every single of this. So the space charge and electric field profile. This is the first publication with the TCT on that. Then you have charge collection efficiency and multiplication. Even that you can measure. So this is here. The effective trapping times are here. Mobility measurement is one that is more recent, a very precise study. Here, the trapping times, I didn't mention it, but you can also mention that. And all this is actually doable with this device. So whatever you see here can be done with that. So, yeah, like I said, lately, other materials are getting more and more popular, and we are now trying to get the hand on the correct laser diodes to actually investigate also these devices. Let me now show you how it looks. I have to. Oh, that was supposed to be an animation, so I'm not sure why it doesn't want to. Okay, it's here. So I will now play a video, and in between we will discuss a little bit how the system looks like. So this is how you set it up for operation. So what I'm connecting now is the power supply for the Peltier. There you have a Peltier. I will come to that later, which cools the surface. So you can actually explore the temperature range between 60 and 0 degrees C. Of course, this depends a little bit on the condition in which you operate sensors, because you can have some moisture on it. But this is the idea. Now we connect the oscilloscope or the digitizing board, which you see here. So this is the trigger, that is the signal. Then we connect the laser bias. The laser power supply actually also supplies the power to the amplifier and filters it. So this is the filter here. The high voltage is actually something that you need to have to operate it, but you can, if you do the exercise, you can also use the normal batteries. You put, I don't know, 5 of them or 6 of them together, depends what voltage it is, and you can then operate it. So what I'm showing here is the filter. So you can tune, and I will show it later in the presentation, the laser intensity electronically, of course, but you can also reduce it even further with the neutral density filter. So what you see here is the pulse. Here is the pulse of the coming from this measurement from this sample now. It's already running. Okay. Let me. Oh no, this is still the same slide. Okay, so we are coming now to just show it from different angles. So this is how it is connected at the back. So this is the filter, this is the digitizer, this is the power supply for the laser and the amplifier. So everything connected in the back. So this is the laser, this is the sample. It looks like that. So the housing of the sample is basically a Faraday cage. You glue or you fix your sensor in the middle and you wire bond it, or you can also use pogo pins, but they're a bit less optimal. If you want to have very nice signals, it's good that they're wire bonded, but you can also use the pogo pin. So what I may have missed, but we'll see it later, is that the amplifier and bias T are hidden behind the laser on this side here, and everything is really very close together, so no long cables, and this actually helps a lot in getting less noise in your system. So another one is to show you, this is the cooler. We have air cooling of the Peltier. Like I said, there is a Peltier board, and I deliberately run it here to 0, that you see that you get some moisture on it, because it gets to actually 0 degrees C. So I don't advise you to do that, or use nitrogen or dry air to actually blow it in the box if you want to go that low, below the dew point. But this is it. So this is the amplifier and the bias T, and see how everything is connected in the box. So pay attention to here. This is the mounting plane. The mounting plane allows you to mount whatever has a lot of holes, and also places where you can put the connectors, and it's cooled by 50 or 75 watt Peltier. So actually, if you are able to cool it well, the hot side, you can get even below 0, right? So it's 0 is something that you easily reach, but you can go well below. But like I said, you have to avoid condensation and freezing. Okay, so let me come to the filter. So there is, like I said, this is the filter, which has multiple grading. You can use anything you like. So in theory, you can get with the system to few photons, basically. You set the laser to the intensity, which is very low, and then you can use additional filters to actually come to almost single photon level. Okay. Let me move on. So why we call it compact? It's shown here. Everything comes in such a suitcase. So this is the digitizing board, which is not really the part, but you can get one. Or you use oscilloscope, and the rest is really well packed. If you have batteries, even the power supply comes inside. If you use the batteries for demonstration, it comes here. So it's really, you can take it, and it's a very powerful measurement technique in one small box. Let me show you now some examples of data taking. So this is the data acquisition software. It has two parts. One is the control of the laser. The other is the control of the data acquisition, voltage source, scanning over the voltages. And like I said, in this particular study, we illuminated this part here. And let me just show you. And in between, I can explain a few things about. So this is what we are using here is the DRS, PSI DRS digitizer, as you see here. It is really, I think it's in the high energy physics, it's a well-known device because it's relatively affordable and it's well integrated. It's quite fast, and you can see its use in many examples. Even Caen builds it in their commercial digitizers. So now we are setting the voltage. So we use Kitely 237 in this case over the Visa, and this data acquisition supports several modes of operation. In compact TCT that we are looking at today, we use the ASCII data format. I will show you the data format later so that it's easily loaded into any data analysis framework you are using. We'll come to that later. So this is how the pulse look like at 10 volts. We set it to 10 volts. This is again the same sample that was shown in the previous analysis. So this is the P on N sample, high resistivity. You see, we inject in low field at 10 volts. It's not depleted, and therefore you have this long tail. I deliberately stretch it so that you can see how long the tail looks like. So this is the electron movement on the other side of the diode. So, and the pink signal here is actually the trigger signal, and laser is operated at 500 hertz. You can have the laser itself can be, of course, you can trigger it with the data acquisition software, but if you want to go to super high frequencies, you can also supply TTL trigger, so the outside trigger. You see, this is how a single pulse looks like. This is the averaging over 200 events. And now we'll see how for example, in this case, how one of these voltage scans look like. So you'll see how the pulse actually changes. So we go from 0 to 100 volts on this device. Remember, the full depletion is around 1820 volts. And we go to 200 volts, and you will see how the pulse changes. And what I just explained you a short while ago, you will be shown also on the display. So we set the laser intensity, which is right here. I don't want to go into details what these numbers mean, but it just changes the pulse width is actually something that changes the intensity. So if you change that, you get more signal. You see now it's getting larger, but we'll use the standard setting for this voltage scan. Now we set it to 500, and then we do run the scan. Now you see, this is the interesting thing. If you increase the frequency, you don't see any change, and the reason for that is very simple, because what you're observing is a single pulse. So what would change if you look at the longer time scale would just be the number of these signals. But each signal should be independent of course, on the frequency. You can test if you have a high rate environment. So if you have pulses in your experiment, or if you want to use it for some specific study, you can set it up to, I think it goes to 1 megahertz, can be used electronically. If you want to have high frequency, you need to do external trigger. Now, this is just to save the comments, to switch on and off the trigger pulse. Let's say that we, in this case, we will not use it. So or if you don't use it, you have to select these channels that you record, and now we'll run the scan. So now it goes to 0. What you actually see is flat line, right? So no signal because there is no field. And then as soon as you start biasing the sample, you see the signal increases. Now at 20, it's already depleted, and you can see that the drift ends here. It's not exponential anymore. And then the higher the bias goes, the higher the current and shorter the signal. But remember the integral, so the charge is the same. And you can clearly see the shape of the field, so it's coming from the high field to low field. For educational purposes, the best device would be the one that has really very low space charge so that you can clearly see all these effects. But in scientific use, it's often the other way around. What I forgot to say is that the software supports actually almost all power supplies that you find in normal labs, so all the Kitleys, also some Agilent ones, and so on. And the same is true also for the oscilloscopes. So you can connect LeCroy, Schwarzenrode, and Tektronix to it, as well as these digitizers. And you can clearly see that once you are very high with bias voltage, you'd stop. This increase is almost negligible. It looks like flat because the drift velocity is saturating, and this is something that also students, when they do this, they actually look at it. Okay. We go to another example. This time that was a red laser, right? So now have a look at the infrared laser. So it's basically the same thing. It's going to be a lot quicker than the previous one because you already know the details about the software. So like again, the frequency, the voltage, now we will run it. See again, no signal at zero bias. You can shift the trigger in and out, so where you want to have it. You can also, if your trigger has a jitter, sometimes some digitizers or oscilloscope have, you can correct it in the software also, so that you get very, very fast rise time, so no jitter or minimum jitter here. And then what we will do, we will set now the voltage scan. What is interesting here, maybe you noticed that the polarity, or you haven't noticed, but you will notice it now, the polarity is different, and the reason is because we are using, in the previous example it was 35 decibel amplifier, now is 53 decibel amplifier, and this one is inverting. So that's why don't get confused about the polarity. So this is what we are actually simulating. And now we'll run the scan. So we check all these values. We use this average TCT. So we are averaging, we are not taking individual waveforms. This can also be done. And just to remind you that this is a 15 kilo ohm centimeter diode, right? So it's a high resistive one. Okay, we can really clean the comments, and now we start the data tagging. Again, you will be able to see basically the textbook example of how the induced current looks like in a silicon diode. So at 0, you get, at -10, it's not depleted, you get this long tail, yeah? And then at 20, you still may not see that it's fully depleted, but then at 30, you will already see that this here ends, and you have this linear part here, is here, and the other linear part is here. So you see this nice textbook example of how the current should look like for the infrared. And it's really like, like a textbook. And of course, then you save the measurements, you select the name for the file. This is all standard, right? So, okay, let's move on. So one of the features that I think is very useful is actually the laser. Maybe I'm not. Maybe I can skip the whole thing. So what the laser offers you is a single pulse any frequency you like. You can use it externally with, like I said, TTL, with faster, but you can also program train of pulses and then decide on which one you trigger your data acquisition. So this is very useful, for example, if you study some saturation effects in your semiconductor and things like that. So it offers a lot of versatility, the controlling of the laser, the electronic one. So. Okay, so the data analysis, like I said, this is how the ASCII files look like. So you have the head, you have the tail of the file, which is below with all the comments that you wrote, and this is the head. So this is the temperature, the starting time, the time between 2 points, the number of points, the number of voltages. Then you have the temperature. It wasn't measured here, so it's all 0. Then you have the voltage points, and then you have the curves in columns, and you can load that in any tool which you like. What we actually advertise or propose to use is the comprehensive analysis library, which is available in root on any platform, operating system that you like, which already has all these analysis techniques that I showed built in. So you load the file and then you can say what you want and it will do it for you. So this is something that handles the analysis, the processing. I didn't go into that. So how you can deconvolute your signals for electronics and all this is possible. It's a bit too deep. And then visualization and the storage, and you can have a look at the library. The link is here. Yeah? So all the analysis plots shown in this presentation were produced with the software. So this is just a comment. So, and I think I'm just about in time. So many thanks for your attention and listening, and questions are welcome.